Welcome back to a continuation of our discussion of the mysterious stuff of which the universe consists. In the last two lectures, I provided for you now compelling evidence for the existence of dark energy, a mysterious sort of substance that causes space itself to expand ever more quickly with time. This is really, really weird stuff, and it's shaking the foundations of theoretical physics. Either there is this dark energy in the universe, or our whole conception, our whole framework is wrong. Either way, things are changing in physics as a result of this astronomical discovery. Shortly after we announced it in February of 1998, theorists got together in meetings to consider, to ponder the missing energy of the universe. Well, again, it's not missing, it's there, we think. It's just of unknown origin. And it was given all sorts of names: vacuum energy, quantum energy. Here you can see funny energy in the universe. Now, what is the universe? Well, it's the universe, of course. Theoretical physicists are quite brilliant, but sometimes they can't spell. Or maybe this is a typo or a right-ho or something like that. But anyway, what is this funny energy in the universe that pervades all of space? There are many possible candidates, and some of them are shown on this view graph that was shown at the meeting in Chicago. The simplest example is Einstein's cosmological constant, lambda, which itself is of physically unknown origin. But there are many, many possibilities. And in this lecture, I'd like to discuss some of those possibilities with you and to show you, to give you at least a taste of what it is that theoretical physicists are considering these days. Now, this is going to be a pretty intense lecture. I'm just trying to give you a general idea of what we're thinking about. Don't worry if the details are obscure. Just get the general idea of what I'm trying to say. To some degree or another, the details are obscure to all of us, because when all is said and done, the bottom line is we still don't know what this stuff is. And there are hundreds of possible candidates, but all of those theories may be flawed in one form or another, and none of them might apply to the real universe. We just don't know at this stage. Well, in general relativity, there are two sources of gravitational attraction. One is already familiar to you: the normal gravitational attraction that matter exerts for other matter. The Earth pulling on an apple, for example, makes it fall. So the mass of an object is the important thing. In particular, the mass density is important, the mass per unit volume. In Newtonian gravity, all that really matters is the mass of one object, the mass of the other, and the square of the distance between them. That gives you in its entirety the gravitational force between two objects. But in general relativity, it's more subtle. As I mentioned, it's the mass density that's important, and moreover, it's pressure. What do I mean by pressure? Well, the Earth exerts an outward pressure on me, keeps me from falling into the center of the Earth. In general relativity, unintuitive as this seems, outward pressure corresponds to an extra inward gravitational pull. It sounds weird. There's no example that I can give you easily in this room or elsewhere that demonstrates this, but it's true. I weigh a little bit more on the surface of the Earth when we consider the pressure pulling me down, the general relativistic pressure, than if we were to ignore this. If we were to only consider the mass of the Earth and figure out what my weight should be, we would get slightly the wrong answer, because the pressure adds a little bit of extra weight to me. It pulls me a little bit more. Positive outward pressure has inward gravitational effect in general relativity. Now, normally this effect is essentially negligible, because the Earth doesn't have much pressure. But on the surface of a neutron star, for example, where the pressure is large, the effect is measurable. And indeed, for the most massive stars, their mass is limited by an instability triggered by the extra gravitational pull of their outward pressure. It's weird, but that's general relativity. Well, now suppose that you have the expansion of the universe that you're trying to consider. In general relativity, applying the concepts I've just discussed in the same way to the whole universe, we find that the change in the rate of expansion of the universe is proportional to the negative of the sum of the energy density, rho, times c squared, plus 3 times the pressure. That sum, take the negative of it, the rate of change of the expansion is proportional to that. Now, for normal types of matter, both rho, the energy density, and p, the pressure, are positive. So the rate is negative. That is, the universe slows down. Its rate of expansion slows down because it's negative. The rate of change is negative. But suppose the pressure of a substance of the universe were negative. Suppose it were less than 0. And in particular, suppose the pressure were less than minus 1/3 of the energy density, rho c squared. Then the sum, rho c squared plus 3p, would be negative, and the negative of that would be positive. And that would mean that the expansion of the universe accelerates, speeds up with time. So if space were filled with a substance of negative pressure and sufficiently negative to overcome the positive energy density, the net effect on the universe would be repulsion. We think the dark energy is something like this, something with negative pressure. Now, this is reminiscent of the stage of the universe's history known as inflation, a very rapid, short-lived time in the universe's first blink of an eye of its existence, when the universe expanded extremely quickly, much more quickly than in the standard Big Bang. It expanded exponentially fast, from something arbitrarily small to essentially an arbitrarily large size. I discussed this concept of inflation at length in my first course in 1998, and I'll discuss it some more in the final lecture of this course. But suffice it for now to say that if you plot the radius of the currently observable universe versus time, right now, here and now, is around 14 billion years. The universe has some size, 10 to the 26 meters, something like that. But in the past, it was smaller. And according to the standard Big Bang, it was sort of smaller and smaller and smaller as you go back into the past, but it was never extremely small. According to inflation theory, it was extremely small to begin with. Then it had a growth spurt, and only later did the regular Big Bang expansion of the universe commence. We think that this inflationary period was driven by a dark energy analogous to what we are seeing now. So already we have some evidence that some forms of dark energy exist, if this inflation theory for the universe is correct. Now, what could it be, this dark energy? What could be the source of this negative pressure? One idea, and the one most closely related to the cosmological constant itself, is that according to quantum physics, the vacuum itself, empty space, is teeming with activity. There are particles and antiparticles flitting into and out of existence all the time, all around us, everywhere. It must be doing that. The vacuum must be doing such a thing, according to the foundations of quantum physics, the Heisenberg uncertainty principle, named after Werner Heisenberg. The uncertainty principle says that you cannot know the precise energy of a point at a fixed time with infinite precision. In other words, you can't know that the energy of every point of the universe is this and that and so on and so forth. That violates the Heisenberg uncertainty principle, which says that the uncertainty in the energy multiplied by the uncertainty in the time has to be comparable to Planck's constant, a very, very small number. And in fact, if you have precise knowledge of the energy of the universe, that is, that it's zero all the time, this is a complete and direct violation of Heisenberg's uncertainty principle. So since you can't have complete knowledge of the energy, nature herself can't have complete knowledge of the energy of every point in the universe. Turns out that might not be obvious to you, but it's true. Nature does not know. That means the energy of every point in space must be continually changing with time. And the way it does so, according to the uncertainty principle, is by producing little packages of energy, delta E, out of nothing for short times, delta T, such that the product of the two is smaller than or comparable to Planck's constant divided by 2 pi. This is a temporary quantum violation of the classical law of conservation of energy. Little bits and pieces of stuff are coming into existence for very short amounts of time, and then they disappear. This is not a violation of the classical law of conservation of energy, but rather it's a quantum violation. It's just on short time scales. However, these little bits of stuff that come into and out of existence do have an effect on the universe. Here are some examples of what can come into and out of existence for short amounts of time. Electrons and their antiparticles, positrons. Protons and antiprotons. Neutrinos and antineutrinos. Quarks and antiquarks. They come into existence, live for a short time, and then annihilate each other. And so on and so forth. This is happening everywhere, all the time. And virtual photons can come into existence as well. I call these particles virtual because they don't live for a very long time. And they're there only because of the uncertainty principle. Nevertheless, they are there. And they affect things like the structure of atoms. If you look at the energy levels of the hydrogen atom, for example, schematically shown here, the outer levels have a greater energy than the inner levels. 1, 2, 3, 4. But it turns out that if you ignore the fact that empty space, as well as the space within atoms, is continually creating and destroying little tiny particle-antiparticle pairs, virtual particles, you get the wrong answer for the theoretical calculated energy levels of the hydrogen atom. You get the wrong answer if you do the mathematical calculation without including the quantum effect. If you include the quantum effect, the energy levels shift ever so slightly, but they shift into agreement with the measured energy levels. And the experiment is correct. That is reality. Theory agrees with reality when you include the quantum violations of energy conservation, and theory does not agree with reality when you ignore them. This is an effect known as the Lamb shift. Another way to see this is that in a diagram known as a Feynman diagram, you can have time going along the vertical axis and space along the horizontal axis. Two electrons that repel each other actually tell each other of their presence by exchanging a virtual photon. A fake, like quantum of energy, goes from one electron to another, telling them to repel each other. I mean, it's fake only in a sense of the word. It's real. It's real at the quantum level, but it's not real at the classical level. Virtual pairs of particles and particles zipping back and forth are exchanged among classical, truly existing particles like electrons or protons. And this whole area of physics is known as quantum electrodynamics. And Richard Feynman was one of the inventors of this new type of physics, and he won the Nobel Prize for this discovery in 1964. Well, it had always been assumed that for every positive violation of the conservation of energy, there's a negative one. So for every positive energy electron-positron pair, there's a negative energy one. In a sense, you can think of one coming into existence by borrowing energy from the vacuum, leaving a negative energy state in its place, a hole in a sense. And all the bumps and the holes fill in together to give you no energy in total, no net energy per unit volume. So it was always assumed that the cancellation is perfect. But suppose it were not perfect. Suppose the positive fluctuations slightly outnumbered the negative fluctuations for a net positive energy density. Then it turns out that these vacuum fluctuations have exactly what is needed for an accelerated expansion of space. That is, they have a negative pressure. A positive energy density in these vacuum fluctuations gives you a negative pressure. And in fact, the pressure ends up being the negative of the energy density, rho, times c squared. So when you substitute this value for P into this equation, you find that you get a positive number, and therefore the expansion of empty space accelerates. If empty space is filled with virtual particles, quantum fluctuations that don't cancel out, then you get the desired effect. Weird. Is this weird or what? Okay. Well, you might say, what is the experimental evidence that there could be different energy densities in the vacuum that have different pressures? Surely you jest. No, I don't jest. There's an effect known as the Casimir effect. You can place two highly conducting metal plates that are well grounded, so there are no free charges floating on them, place them close together, and they have negligible mass, so you don't have to worry about their gravitational attraction for one another. You put them close together in a vacuum, and what do? They slowly go towards each other. In a vacuum, massless plates with no electric fields around that you can tell move towards each other. Why? Why do they do that? Well, let's take a look. Here I've shown these two plates close together, a distance L from one another. It turns out that outside the plates, all sorts of wavelengths can occur for all these particles that are appearing and disappearing in space. Every particle, according to quantum mechanics, has a wave associated with it. And all possible wavelengths exist outside the plates. But in between the plates, only certain wavelengths are permitted. You can fit a half wave between the plates, or one full wavelength, or 1.5 wavelengths, or 2, or 2.5, or 3, and so on. The distance between the plates must be a half integer multiple of the wavelength. That's a boundary condition. An example of this is that in a wind instrument with two closed ends, the molecules can't vibrate at the ends. They can't vibrate back and forth because there's a wall there. So only certain sound waves are allowed within the instrument. You can't have all possible waves because to have all possible waves would require molecules to be zipping back and forth at a place where they cannot do so because there's a wall in the way. So you get standing waves, sound waves, in these instruments. Now let's look back at our diagram. This is exactly what we see in the Casimir effect. Only certain waves are allowed, whereas outside, all waves are allowed. There are more of them outside than there are between the plates. Yes, there's an infinite number between the plates because you can make them smaller and smaller and smaller as long as there's a half integer multiple of them. But that's still a smaller infinity than the infinity that exists outside the plates. Uh-oh. Now I'm talking about infinities again. Didn't I confuse you enough already when I talked about the rational numbers and the counting numbers being the same size? Well, now I'm going to show you an infinity that's bigger than the counting numbers. And indeed, the infinity of waves outside the plates is bigger than the infinity of waves inside the plates. And so there's a pressure produced by all these guys outside the plates that's bigger than the pressure of the waves inside the plates. And so that's the pressure that pushes the plates together. It's a quantum pressure due to the difference between one infinity and another infinity. Let me show you. Let me show you what I mean. Recall the rational numbers, which I said were a countable infinity. You could number them all and keep track of all of them. Even though there's an infinite number of rows and an infinite number of columns, there's a system for keeping track of all of them. I showed you that if you go along diagonals like this, you will not miss any of the numbers. Just keep on going forever. It's pretty boring, but you could do it and not miss a single one. That is a countable infinity. However, there are infinities that are mathematically uncountable. They are larger. The most famous example are the irrational numbers. Square root of 2, pi, e to the pi, square root of 2 to the pi e. All those numbers are irrational. They cannot be represented by a fraction in this way. They are a bigger infinity than the counting numbers, a bigger infinity than the rational numbers. Here's the proof. Let's consider just the interval between 0 and 1. We suppose, this is going to be a proof by contradiction, so we suppose that you can list all the numbers sequentially in this interval. Let's call the first one 0.A11, A12, A13, and so on, where the A's are simply digits between 0 and 9. So A11 could be 1, A12 could be 7, A13 could be 5, A14 could be 0, and so on. Next number in the list, A21, A22, and so on. Next number, and next number, and next number. You suppose you've written them all down by some scheme. You suppose you've counted them all. I will now show you a number that is not in that set. It is demonstrably not in that set. I can construct such a number quite easily. Let us write 0.B1, B2, B3, B4 with the condition that BI is not equal to AII. What do I mean by that? What I'm saying is B1 can be any number you want, 0 through 9, as long as it's not the number here, A11. Suppose that number were 5. B1 could be 7 or 0 or 9 or 6. It just can't be 5. So already my number differs from this number. B2 can be any number you want, but it differs from A22. Suppose A22 is 7. B2 can be 0 or 9 or 5 or 6 or 3, but it can't be 7. B3 can't be the number A33, and so on and so forth. I have easily constructed a number which by construction differs from every single number that I have listed in my list, right? Therefore, the list was incomplete. Therefore, the list was incomplete, and I have found some numbers that weren't in it, and therefore this infinity is bigger than the infinity of rational numbers. This is Cantor's famous diagonal proof for the larger infinity of the irrational numbers compared with the rational numbers and the counting numbers. All right. Well, the infinity of waves outside the Casimir plates, being unrestricted, unbounded, is bigger than the infinity of waves between the plates, which can be counted by the integers. And the difference in those infinities leads to a pressure on the plates. Between the plates and outside the plates, you have a vacuum. But the vacuum between the plates is less energetic than the vacuum outside. This example is meant to just illustrate for you one possibility for how the vacuum can have an energy and still be a vacuum, and an energy that differs from an energy that might be elsewhere. Okay? I'm not saying that this is what's happening in the universe to make it accelerate, but this is an example of what could be happening to illustrate the physical point. So, the vacuum fluctuations, lambda, could be such a property of space where you have an energy density that's greater than 0 and a pressure which is less than 0, and that causes space to stretch and stretch and stretch. And in fact, as the amount of space grows, the total amount of energy of this stuff increases because the volume of the universe is growing. And every bit of volume has this energy, has these quantum fluctuations. So it seems like the total energy of the universe is growing without bound, from nothing. Looks like I've created energy out of nothing, but I haven't. It turns out that all of this stuff, though it consists of positive energy, it also has a negative gravitational energy associated with it, because it attracts all the other stuff in the universe. And a gravitational attraction is a negative energy. I can illustrate that easily by dropping this apple. Boom, like that. I dropped it from rest, so it had basically no energy to begin with. It had 0 energy of motion, quite obviously, and I can define its gravitational energy to be 0. It's an arbitrary constant, really, is what it is, but let's call it 0. 0 plus 0 is 0. As the apple falls, it gains energy of motion. Looks like I'm creating energy out of nothing. But no, what's happening is, as the apple gets closer to my hand, closer to the center of the Earth, its gravitational energy is becoming an increasingly negative number. -1 unit, 2 units, 3 units, 4 units. At the same time as the energy of motion goes from 0 to positive 1 unit, 2 units, 3 units, 4 units. The positive and the negative cancel out. The energy of a falling apple does not change. And in a similar manner, the energy of the universe inflating in this way does not change. Even though I continually have more and more of this vacuum energy, it is balanced exactly by the negative gravitational energy. This is heavy stuff. I told you, I warned you, okay? It gets worse. All right, so all lengths double in a certain amount of time when you have an exponentially expanding universe. If I take one step and then the space between my 2 feet grows by a factor of 2, the next step I have to take is twice as big, and then a factor of 4, a factor of 8, 16, 32. It doubles. It's an exponential growth. Now, that's not what's happening to the universe yet, because the vacuum energy density does not yet dominate over the matter energy density. Remember, omega lambda was 0.73, omega matter was only 0.27. So it's not like lambda completely dominates over the attractive forces of matter yet. But someday it will. So we're beginning to accelerate, but we are not yet exponentiating. What will happen when we do exponentiate? Let's consider exponential growth in this example here. Suppose I put 1 penny on the first square of a chessboard, 2 pennies on the second square, and so on. Each time, I double the number of pennies on each successive square. On the 64th square, there will be 2 to the 63rd power pennies. Okay? That's 10 to the 19th power cents, which is 10 to the 17th dollars, which is 100 million billion dollars. That's richer than Bill Gates, okay? That is an almost unfathomable amount of money. And it reminds one of the tale where the pauper rescued the daughter of the king from certain death. And the king said, well, I will give you a reward. And the pauper said, okay, give me a gold coin on the first square of a chessboard, 2 of them on the second, 4 on the third, 8 on the fourth, and so on, and that will be reward enough for me. And the king thought, what a dork this person is, you know? And then he tried to do it. There is not enough money in all the kingdoms in the world to fill that chessboard. All right? That's exponential growth. And in fact, when the universe was very young, that's what we think was happening during this era of inflation. When the universe grew from an essentially arbitrarily small size to an arbitrarily large size in a blink of an eye of the universe's existence. That's what we think happened, and I'll discuss it some more in the final lecture of this course. If we are now entering a new inflationary phase, this is what our fate will be. Eventually, the universe will grow exponentially, though it is only slightly accelerating right now. Well, now let's go back to our definition of omega lambda and omega matter. Recall that omega lambda was just some number, the cosmological constant divided by 3h0 squared multiplied by c squared. Omega matter was just the average density of the universe divided by the critical density. There are two problems with this interpretation of what's producing the acceleration. The first is, why is lambda so small? A fairly simple calculation in physics suggests that if our physical theories are correct, and if the vacuum energy does not cancel to be exactly zero, then its energy should be 10 to the 120th power. Omega lambda should be 10 to the 120th power, which is 20 orders of magnitude bigger than a Google being 10 to the 100th power, not 0.73. Now, by sleight of hand, you can get the expected value for the vacuum energy to be as small as 10 to the 50th power. That's still a very large number compared to 0.73. We measure it to be 0.73. This is a huge discrepancy. The discrepancy was known even before our measurements with the supernovae. We've known that omega lambda can't be bigger than about 2 or 10, otherwise we wouldn't exist. The universe would have spread apart so quickly that we wouldn't exist. So physicists had always assumed that when the final theory is done and completed and all figured out, there will be some deep reason for a perfect cancellation between the positive and negative energy fields. Kind of like this borrowing concept that I discussed earlier. Physicists expected there to be a perfect cancellation. They don't understand why yet, but they fully expected it to be true. For us to find a nearly perfect but slightly imperfect cancellation was to them inconceivable. This was like the worst error ever made in theoretical physics. You expect the number to be a Google or more. It ends up being not quite zero, for which you might have a solution, but almost zero. Theorists were incredibly surprised. In fact, when I gave a talk at a meeting in 1998, one very eminent theorist told me that our observations must be wrong. We're wasting telescope time. The universe can't possibly have a nearly zero, but not precisely zero energy density on large scales. Well, I said, well, look, I'm an observational astronomer. You theoretical physicists might be very smart, but to me it's an observational question. Either the universe is accelerating or it's not. Either there is some sort of dark energy or something else. We're not necessarily saying it's dark energy. We're just saying it's something. Either something is doing this or it's not. If the observations say that the universe is accelerating, then we have to come up with an explanation, regardless if we haven't yet been clever enough to do so. Now that the WMAP results are in, and now that the supernova measurements are even better, I'm wondering what that particular theorist is working on now, But he said we must be wrong. Wow. The second problem, however, with the vacuum energy fluctuation explanation for the dark energy is one of timing. I said that omega lambda is 0.73 right now, and omega matter is 0.27. The ratio of those two is 2.7, which, for government work is pretty close to 1. Now, you might say I'm being a bit flippant here. 2.7 looks different from 1. But the ratio could have been anything. It could have been 1/1,000,000th. It could have been 1 billion. It could have been a Google. It could have been 10 to the minus 23rd power. It could have been anything. 2.7 is darn close to 1 when you consider all the numbers that the ratio could have been. And indeed, omega lambda used to be much smaller, and omega matter used to be much bigger. They are evolving with time. When the universe was more compressed than it is right now, galaxies were closer together, the box was smaller, but the number of particles in it was the same, so the energy density of the matter was bigger, and there was more gravitational attraction. As the universe expands, especially now that it's accelerating, the number of galaxies is staying the same, but the universe is getting much, much bigger. So the matter energy density is declining with time, whereas the vacuum energy is increasing. Let me show you a graph that illustrates this. Plotting the fractional energy density, that is omega, along the vertical axis versus time along the horizontal axis, you can see that the matter energy density of the universe went from being close to unity, omega of 1, down to only 0.27 or something right now, and it will subsequently become very, very small. But right now is given by t equals 0 here. So here it is at 0.27. The lambda, the cosmological constant energy density, on the other hand, started out small, is 0.73 right now. Here it is, 0.73 right now. And will grow closer to unity as time goes on. So, one energy density grows, the other one goes down, okay? And why is it that we right now are living at a time when they're nearly equal? They were exactly equal perhaps 4 or 5 billion years ago, but right now they are nearly equal out of all the things they could have been. This is a fine-tuning problem, the why now problem, sometimes called the Nancy Kerrigan problem. Why now? Why me? Why is our universe doing this? We would like to have a more natural solution to this, a more natural way of both producing a small vacuum energy density right now and also making it not so apparently coincidental that the vacuum energy density right now is roughly equal to the matter energy density right now. Maybe there's a physical mechanism that naturally explains that and makes it true for a large amount of time, much larger than just the couple of billion years around our current existence. So models called quintessence have been invented. Quintessence refers to the Aristotelian fifth essence, the ether that pervaded the universe. There was the earth, air, fire, and water, and then there was the fifth essence, the quintessence. Quintessence basically says that there's some sort of a field in the universe that we haven't yet completely taken into account, some sort of an energy field. And it behaves in a way that causes the universe to accelerate in its expansion. But it is not the quantum fluctuations that I've been talking about up to now. It's something else, they say. To understand what this might be, we will consider symmetry and the breaking of symmetry. Let's look at a droplet of water floating around in a vacuum in empty space. It's perfectly spherical. It looks the same from any direction. We call it rotationally symmetric. It's the most symmetric thing you can think of, a spherical droplet of water. Now you might think that an ice crystal is more symmetric because there's a hexagonal symmetry, snowflakes and things. But an ice crystal is less symmetric in this sense of the word than a spherical droplet, because a spherical droplet looks the same from every direction, whereas an ice crystal has preferred axes along which it looks similar and other axes along which it looks different. So, ice is less symmetric than water. As you go from water to ice, you have a breaking of the symmetry. And so here I show some ice cubes. When they were in the liquid state, they had more energy. That's what kept the molecules moving around and keeping them in the liquid form in the first place. As the energy was lost from the water, symmetry broke. The hexagonal crystals formed. The energy of the molecules was released into the outside world. Well, suppose you supercool water to a lower temperature than 0 degrees Celsius. Normally it would turn into ice. But if you supercool it and keep it in the liquid state, It has an extra energy associated with it. That's what keeps it in the liquid state. It's got a latent heat associated with it. If the universe had some sort of a force field that cooled below a certain temperature without breaking symmetry, without turning into some other sort of a substance, it would have had a latent heat associated with it. And the idea is that that latent heat expanded the universe and is doing so right now at an ever-increasing rate. That's the idea of quintessence. Now that's fairly foreign sounding. So let me show you an example. Here I have a solution of sodium acetate. This is called the heat solution. You can buy it in camping stores. It's a liquid at room temperature. There it is. It's a clear liquid. But it's supercooled. It would like to be a solid crystal at room temperature. But it's supercooled. And I claim it has a bunch of latent heat sitting around in there, keeping it in the liquid state. If I tickle this thing a little bit by bending a metal disc inside, you can see a phase transition occurring. The liquid is turning opaque. That's because it's turning into a crystal, a solid. And oh man, it's getting hot. My hand is getting hot. I can't hold on to it very long. I'd better hold it by the edges. The latent heat within this supercooled liquid was released upon turning it into a solid, a crystal. And after all that heat is gone, this thing turns into a solid rock, a solid crystal. All right. So there's the idea of a supercooled substance which has a heat associated with the state of being supercooled. In the case of the universe, this inflates the universe and causes accelerating expansion. In the case of the easy heat solution, it does not. All analogies must fail at some point. Every analogy has some flaw. The trick is to know where the analogy is giving you correct information and where it's incorrect. The incorrect information here is that, or the incorrect conclusion would be that the latent heat of the supercooled solution inflates this thing and destroys us all. Obviously it doesn't. So that's where the analogy here fails. But every analogy must fail at some point. Otherwise the analogy would be the exact thing that you're trying to describe. So let's take a look at what happened here. If you plot the energy of a substance versus some symmetry-breaking parameter, call it phi. Perfect symmetry is phi equals 0. That's the liquid water. So at a high temperature, water likes to be a liquid because that's the state of minimum energy. The ball likes to roll down the hill and sit at the bottom of the hill here. That's a state of minimum energy. Broken symmetry at high temperature, above some critical temperature, would be a state of higher energy, so that's not what water does. But if you cool water or easy heat solution or whatever below some critical temperature, the curve describing its energy density versus the symmetry breaking parameter looks something like this. It likes to have broken symmetry, phi not equal to 0. It likes to be like a crystalline substance. It would have more energy if it remained a liquid. But it can remain a liquid if there's a dimple in this curve. It can remain in this little dimple. This is a local energy minimum, not a global energy minimum. The thing would prefer to be down here. But it can, if it's not tickled or disturbed too much, remain in this state where it is supercooled. And this is exactly what was happening to the sodium acetate solution at room temperature. It was in a supercooled state where it had an extra energy. It was sitting in the dimple of this energy curve. That, applied to the universe, is one form of quintessence. Now, there are many, many forms of quintessence. I can show you other curves that describe the kind of universe we might live in. Here's a curve that doesn't have a dimple in the middle. This is a very unstable state. The ball quickly rolls down the hill, it breaks symmetry, and the universe doesn't inflate for very long. But here's another kind of an energy density curve where breaking of symmetry occurs, but there's still a lot of latent heat available to cause the expansion of the universe to accelerate with time. We don't know exactly what's going on, but we think that some sort of an energy associated with a field, a force field or a particle field, of which we have no direct laboratory knowledge yet, but something like that might be currently accelerating the universe and might have accelerated the universe during the inflationary era. There are literally hundreds of models. We're now doing observations of supernovae to try to figure out which model is correct, because each of them produces a slightly different expansion history of the universe. Maybe by the next time I give another course for the teaching company, we'll have a better idea of which form of quintessence, if any, is the correct one.